Good afternoon, everyone. Welcome to our edition of Robotics Seminar. As you know, the talk shifted from Friday to Monday, so thank you, Tania, for being here. Tania is a professor at UCSD. Before UCSD, she did a PhD from Stanford, and before her, she was at MIT. So, welcome back. Her research has won, several accolades, including the NSF Career Award, a Kavli Fellowship, and a Mass Rising Star Award. And I think the list goes on and on. So, without further ado, Tania, welcome, and looking forward to your talk.
Great, thank you, and yes, thank you guys for being here. I know that there was some travel issues, so I appreciate you guys showing up. And I'm very excited to be here today to talk about some of the research in my lab, particularly focusing on a lot of our soft robot design, as well as some of our haptic interfaces and more wearable systems. So I like to start by showing a little bit of what I see as kind of the landscape of medical robotic systems today, both for surgical robotic systems as well as for more rehabilitative robotic systems. So if you look here sort of on the one end of the spectrum on the left, we have what I see as these more kind of manual tools, manual instruments, manual methods of performing these types of either surgical procedures or rehabilitation. And so you can see sort of on the top for surgical robots, oftentimes what we have are these manual laparoscopic instruments that go inside the body. The surgeon, has to manipulate them. The kind of mapping between the user input and what happens, inside the body is rather non-intuitive. And then you also have for rehabilitation, for example, actually going to a physical therapy clinic and having someone maybe even manually move your joints through different range of motion exercises. And then on the other end of the spectrum, we have our robotic systems. So for example, we have various surgical robotic systems that can help with minimally invasive surgery. It's really nice for the surgeon. There's this kind of more intuitive mapping between user input and what goes on inside the patient's body. You can have better control. You can do things like scaling, right? You can have larger scale human motion mapped to smaller scale motion of the robot. And in terms of rehabilitation systems, you have a lot of systems inside the clinic. But what I see is kind of this gap in the middle where we have these nice manual methods and we also have these pretty large scale robotic systems that tend to take up quite a lot of infrastructure space. They're quite costly. Most of them tend to be rigid robotic systems, although we're seeing kind of a trend towards some more flexible ones. And so I think that there's room for something in between here, maybe for environments with lower resources that could kind of fit in between. So that's kind of what my research lab has been focused a lot on, is how do we fill this gap? And it doesn't necessarily need to be, instead of these. I think that could be seen as complementary as well. But we work on both sort of the patient side robot, so either the surgical robot or the rehabilitation robot, as well as the human control interface. And so how do we actually teleoperate and control these soft robots? And we think about this in terms of haptic interfaces in particular. So how do you have intuitive user input into the system, but also get force feedback maybe back? And so in particular, we focus a lot on designing new soft robotic systems, thinking about how do we enhance the capabilities of these systems that already exist. How do we create new intuitive user input devices that can also provide meaningful feedback to better control the robots? We think about sensing. How can we actually sense robot position, shape, right, forces reliably and accurately? And how do we come up with better control methods for these robotic systems that can work even in very unconstrained, dynamic environments? So in particular, inside the human body, right, it's a much trickier type of dynamic, uncertain environment than maybe a factory floor. And so in general, these are kind of the areas that my lab focuses on. I won't have time to talk about all of them, so mostly I'll be focusing on kind of the first 2 points here. And I've kind of structured the talk in these 3 main areas. So the first is thinking about these soft continuum robots or snake-like robots that can enable navigation in highly constrained environments. And because they are soft, they can kind of conform to the environment. They can navigate these highly curved paths. So I'll talk a little bit about some of our work in this area. We're also thinking a lot about soft wearable devices. So thinking more about how can we create these devices that can be worn more like clothing, could maybe be used in a more at-home setting, can be more comfortable, and maybe can be used for rehabilitation outside of a clinic. And then finally, I'll talk a little bit about some of our soft haptic interfaces. So things that could also be worn, for example, can provide force feedback to the user, information on maybe the task or the environment, or could provide guidance as they're trying to teleoperate some of these different types of robotic systems. So this is kind of the three main areas that I'm going to talk about today. And I'm going to start with talking about some of our soft continuum robots. So yes, I'm going to talk about a few different types of robotic systems, focusing on first some of these continuum robots. Okay, so here is some older pictures, some history from various surgical robotic systems that have been developed over the last several decades. There's a number of different systems. Some have been developed, commercialized, some are still in existence, some are not. But in general, they've all been built with varying number of degrees of freedom, different types of operations. But there's a number of advantages, kind of as I mentioned before. But one thing I want to point out is this recent trend towards these more flexible robotic systems. I'm not sure if people have seen these or are familiar with them, but Intuitive Surgical's Ion robot for bronchoscopy, Monarch, Corindus, some of these newer systems tend to use these more flexible kind of catheter-like systems. And this has kind of been a more recent shift, and they can be quite minimally invasive and can access places sort of deep inside the body. And it's really these types of flexible, soft kind of continuum robots that my lab is focusing on. And so here's kind of what we've been thinking about is really how can we create these safer and more dexterous robotic systems for navigation in these highly constrained environments. And in general, what these continuum robots have in common, right, are they these long, slender form factor. They often inspired by biology, from snakes, from elephant trunks, to tentacles of octopus. And there's a number of different benefits, including being able to conform around these highly constrained environments, take tight turns, and their inherent compliance can make them a bit safer for operation near humans or inside humans. There's been a number of different actuation architectures that have been proposed. I'm showing a shot from a review paper here that shows different methods of actuation, right? We can use tendons, pneumatics, hydraulics, mechanical interaction between the tubes themselves. And what I'm going to focus on today is some of our work on these vine growing robots or everting robots. I see some nods. Maybe people have started to see these. I think they've become quite popular over the last several years. The idea is very simple. You can see a video of one in the bottom corner. So it's simply a thin-walled hollow tube. We form it into this tube. It's usually made from some sort of plastic, or sometimes people make it from a fabric material. You take this tube, you take one end, and you stuff it back inside the body of the tube. Then as you pressurize it with air or water, you can see that the material basically everts or extends out the tip, but the body of the robot is not moving with respect to the environment. So if that makes sense, you can see the lines that we've drawn on the body of the robot. So this means that even as the tip moves forward, we have no shear forces with respect to the environment because the body remains stationary. And so you could imagine this could be very nice, particularly for some type of medical application, where instead of taking a traditional catheter, where you're basically pushing it through the blood vessels, or a colonoscope, right, any of these tools, where you have to load it axially from the base, now we can achieve this forward locomotion without these sort of shear forces. So in theory, the idea is quite nice, but in practice, if you want to start to think about how can we make these to actually be useful for medical applications, it becomes quite tricky, right? Now, having just a hollow tube that gets somewhere is not really enough. We want to have access through the middle to have some tool, maybe a gripper, maybe something to grab a blood clot. And because of this vessel is pressurized, it means this internal material is pushed against itself. And so you actually can't really slide a tool relative to that very easily. So kind of including a working channel is hard, and so is steering. How do we steer so that we can get to where we want to go? And how do we do this all at a very, very small scale? So this is kind of one big challenge my lab has been focused on, is how do we miniaturize these? And what we did first is started to think about the scaling of these. So if we isometrically scale these radially, and we start to think about scaling these down to sizes that are relevant for medical applications, so more on the millimeter scale, what we see is that as we isometrically scale this cross-section, so the radius, the working channel, the thickness of the material, we can see that this growth pressure, the pressure required to grow the robot, is going to increase. And if we try to grow over very long lengths, our pressure is also going to increase. So this becomes a challenge, right? If you want to have a really, really tiny robot that can actually navigate, say, through the colon, through your blood vessels over a long length, this becomes a hard problem. If the pressure is going to increase, at a certain point, your robot will probably burst before it will grow. And so this is kind of the challenge that we've been starting to think about how to overcome. And it becomes even harder if you're trying to go through these highly curved paths as well. So we have a few different approaches to try to solve this. I'm going to show one example here. So one idea was basically, what if we take all that inverted material, and instead of allowing it to run along the entire length of the robot, where now your friction is going to increase significantly as the length increases, what if we take all that material and we actually scrunch it or stuff it up at the tip of the robot? Now our effective length of friction here is much, much shorter. And so we can actually enable a significantly longer growth length just by this very simple sort of change in the design. And so now we have this contact area between the Vine robot, this kind of inner material, and this working channel, as well as contact between that and the body. And now we've shortened it, and so we can grow much longer lengths. And so you can actually see kind of an animation we made here of what it looks like as we kind of unfurl this scrunched material just from the tip. And this is an example of what this can enable, is now if we take a robot that is about the size of a colonoscope, so it's just over 1 centimeter or so in diameter, and we have a working channel of about 4 millimeters, we can actually grow for 1.5 meters long, which is what you would need for a colonoscope. So it actually enables these robots to be much more practical by just reducing this effective friction length. And so we have some modeling that looks at this, so looks at what happens if we have kind of our standard Vine robot with a working channel versus if we now have this material all scrunched up at the tip. And we both modeled it and then looked at the experiments both in straight paths as well as at the bottom, you can see in curved paths. And what we can see is that if we have kind of this standard approach, we can really only grow about 40 millimeters or so, versus we can grow 1.5 meters long if we do this kind of scrunched approach. So really this increase in growth length of over 40 times, so really trying to make these robots much more practical compared to what exists. So that's one way we've been thinking about kind of the miniaturization and making these robots more practical. But the other area we've been focusing a lot on is how can we actually functionalize these robots? How can we steer where we want to go? We don't just want it to follow maybe a given path. We want to be able to control in real time what direction we're actually growing and bending. Now, steering is quite challenging. These types of robots, you can imagine that because this material, the material at the tip is always changing, right? The physical material, because of this growth mechanism. Integrating steering is quite different than if you had a standard kind of tendon-actuated robot, maybe. And so we've been thinking about, and how do you do this at a very small scale? So I'm showing just a few examples from our lab here before I go into one project in more detail. So up at the top left, you can see a video of a pre-curve design. So this is an example of passive steering. Say we have preoperative images of a patient, or we know the environment we're trying to navigate, we can actually pre-design these curves into the robot body. So as it deploys, it takes on a known shape. And so that's one example. Below that, you can see an example of integrating a very small tendon inside the working channel. You pull it, that's going to make it bend, and then you can continue to grow from there. At the bottom, we can see a pneumatic approach. So here's just putting 3 pneumatic artificial muscles around the circumference, and by pressurizing them differently, we could get bending. Up at the top, this example here actually has a robot inside the robot. So it's a little inchworm robot, and it basically can crawl its way inside of the growing robot. It can bend to steer the robot, but it can also actually grab this inverted material and pull it back inside itself to enable perfect retraction of the robot as well. So it turns out retracting the robot back is actually very hard to reinvert this without making it buckle. So this is one approach. And then the very last video here is of a magnetic approach to steering. So we can embed these magnetic material into the skin of the robot. You can bring a permanent magnet towards it, and we can actually get steering of the robot body as well. So these are all potential steering approaches we could take. They all have their trade-offs. I don't think that there's one design solution that's maybe the best for all applications. But in general, what I want to say here is that steering at this scale is hard, especially with these thin-walled materials. Yes?
And as you scale them and they become more elongated,
yes.
Their power also reduce or their strength also reduce? Or do you assume that there's some excess material which is always there?
Yes.
They keep pushing through so that it can still retain all the properties.
For like the steering, and yes, this is a good question. So there are challenges with steering over these long lengths, especially for any sort of tendon actuated system. You can get especially if you're in curved paths, you can get a buildup of this friction. And so that can become quite challenging. So yes, there are challenges as you start to scale, both in length as well as in diameter. So actually the approach that I'm going to show, I think, could kind of help overcome some of these types of challenges. Oh, I did bring an example of it too, actually, so I can pass it around if people are interested. So yes, I think that leads me to the next portion, which is on another steering approach. So I have a small sample if people would like to see it. So here, our idea is to instead integrate a thermally actuated material into the skin of the robot itself. So now we can actually integrate these at discrete points along the length of the robot. And the idea is, as you heat it, this material will contract. And then when you let it cool again, it goes back to its original length. And the nice thing is that these have very high work density, and they are very soft and elastic, so you can keep the robot sort of fully soft, and they can be quite thin, so we can integrate them directly into the skin. So I have this kind of little small example. You can kind of pump it up with your hand if you want and sort of feel it. Unfortunately, you can't. These are the wires to actually heat it. I did not bring that aspect, so you can't actually actuate them, but you can sort of play around with it if people are interested. And so the idea here is, yes, we integrate this liquid crystal elastomer, this thermal actuator, into the skin of the robot body. We heat it, and that one side will contract, and we can get bending. And so here's an example of actually the one that I brought here, bending. And so you can see that we can integrate these all along the circumference at different locations and along the length. And that means that as we grow or evert, we can actually control bending at different locations along the robot body. So the way that we do this is we have to integrate both the liquid crystal elastomer as well as a heater, a way to actually heat this LCE. And so we use this material called P.PSS. That's the black material that you guys will see in the sample being passed around. We run these little copper wires that you'll also see all the way to the base. We apply a current. It will heat this heater, which will then heat the liquid crystal elastomer, and we can get bending. And we can control both the pressure inside the robot body and the temperature of the LCE to control the bending angle. And here's just a few example videos of what you can do with this particular system. So these are about 5 millimeter in diameter, the robot itself. Because the liquid crystal elastomer is soft, we can maintain the softness of the whole body, so we can squeeze through these really tight gaps that are smaller than the robot body itself. And we can continue to grow afterwards as well. Yes?
As far as I know, usually the transition temperatures for the liquid crystal elastomers are likely above the safety threshold for implantable or wearables. How do you work around?
Very good question. So my colleague at UCSD, who we collaborate with, Professor Sai, they actually work on these types of LCEs, and they have the ability to change the chemistry to actually change the transition temperature. So we told them that, for example, for inside the body, we need something that is just above body temperature, and they can fabricate and manufacture that. So it makes it, quite nice. Otherwise, it can be a challenge, as you're saying. Exactly. So yes, here's an example of it kind of squeezing through a gap. Another example where if you put 3 around the circumference, right, now you can steer in 3D. We can put a camera at the tip. You can do these more sort of inspection tasks. And so here is just some simple kind of modeling for the steering angle control. So here, basically looking at just a moment balance. So we have a moment based on the actuation of the liquid crystal elastomer. And then we also have this kind of restoring moment due to the internal pressure inside the robot. And this, again, as I said, gives us two control inputs, pressure and temperature, to control the bending angle. And so we can look at the model compared to our experimental data for both pressure versus the angle, as well as temperature versus the angle. And you can see a few examples. Yeah? Yes, okay, so you're saying, is there a maximum angle where it will instead kink? Is that what you're saying? Yeah, that's a good question. I would say that here, what our limiting factor is just the actuation stress of the material itself. We have noticed that if you try to sort of purposely get kinking, you can get even tighter bending angles, right? But here we were trying to sort of constrain it in such a way that you could have relatively constant curvature bending. But yes, you are still going to be limited in the maximum bending angle. But I think, as you'll see from some of these pictures, compared to other steering approaches, it's quite good in terms of how tight of an angle you can achieve here. Yeah, good questions. Great. So here are a few examples of some of the things that we can do with this robot once we fabricate it. So kind of compared to other steering approaches, we can actually bend at multiple locations, right, along the length of the robot. So by placing these at strategic locations, maybe based on an expected environment, we can steer at multiple points. And these plots are basically just showing that we have different methods for controlling our robot. We can control with pressure only, temperature only, or we can change both simultaneously. The benefit to controlling both is that if we only used pressure and we tried to control the bending angle of a distal actuator, as we modulate the pressure, the more proximal angles are also going to change because there's only a single pressure running through the robot. So by kind of modulating both, we are able to mostly control kind of the shape of the more proximal section. Of course, this is all done in open loop and is teleoperated by my postdoc as he's controlling it. So there is definitely room for some sensorization, closed loop control. But I think for a lot of the applications we're thinking, there's probably going to be a human kind of closing the loop for the most part. But what you can see on the right as well is that even though we have to place these actuators at discrete locations along the length, you still are able to navigate many different paths with a single robot design because it has a relatively large workspace, and each actuator can still be controlled to many different bending angles. So yes, might not solve every problem in growing robot steering, but I think could be good for a number of different applications. So a few of the applications we were looking at, one of them is thinking about medical applications, in particular here, thinking about blood clot removal for stroke patients, so mechanical thrombectomy. In these types of procedures, typically what they will do is they'll take a catheter, they'll insert it through the femoral artery in the hip, and they basically will push and twist the catheters from the base, all the way from the hip, up through the aortic arch, which is the model that you're seeing here, and up towards the brain to remove the clot. So if you can imagine, it's quite challenging to learn how to do this. All you have is pushing and twisting, and it's basically these catheters with like a pre-curved shape to them. You kind of push and twist it. If you can't get it to work, you pull that one out, you put a different one in, and oftentimes it's a number of these different instrument exchanges. So it takes many, many years, if not decades, for people to learn to be very good at these procedures. So something we've been interested in is basically, can we make these procedures a little bit easier to learn so that people can become better at these procedures in a faster amount of time, maybe make it more accessible to people who don't have access to really high quality care in a nice hospital. And so here's an example of this LCE actuated growing robot actually going through one of the trickiest types of aortic arches where there's these very tight curves. And again, this is a single robot design, but you can see in these videos, it's going through 3 different branches, even with the same kind of discrete set of actuators here. And the other thing about this design is not only are we kind of growing to the different locations, we're actually pulling a catheter along with us. So by the time you get to the target location, you can actually pull suction to pull out the blood clot directly. So it's not just sort of a hollow tube getting there, but you're actually pulling a useful catheter. So this is kind of one approach we've been taking to steering, is using these liquid crystal elastomers. But we also have another approach. Again, I don't think that there's kind of one solution solves all. So here, to solve this same problem of mechanical thrombectomy, we have another method. So here, in this design, what we were thinking about is really a lot of the tricky steering happens sort of in the proximal anatomy in this aortic arch. And we can actually use traditional tendons to maybe steer around these paths. And then we could have our sort of growing robot grow through this challenging sort of twisty anatomy afterwards. And again, we are pulling an aspiration catheter to the target site so that we can pull the blood clot. So kind of a different architecture, still taking advantage now of this growing element, but using some more traditional sort of steering methods for the more proximal component. And so with this, I should also mention that with this particular design and for this application, I think a lot of the growing robots you guys have seen are probably pneumatically actuated. Now, if you're inside the blood vessels, you probably don't want air going through your blood vessels, especially if there is a leak or something pops. So we actually grow this one using a saline solution. And here is an example of it in action. So this is a flow model, again, of the same sort of anatomy. And we put in like a mock blood clot. So it's actually just this like Elmer's glue to kind of mimic a blood clot. And you can see here this sort of proximal steering. We teleoperate this right now just with a Xbox controller. We can just do with the joysticks, buttons. We can steer into this portion of the anatomy called the internal carotid artery. And once we get there, we can increase the pressure in the system to basically grow the growing component out from it. And it's, again, pulling this catheter along. So I know it's a little tricky to see. Once that's the catheter it's pulling, you can see it pulls it even through these 360-degree loops of the blood vessels up towards the blood clot. And this is kind of a side view. You can see it a little bit better. But you can imagine that this is quite tricky to do if you're pushing a catheter from the base, but you can see that it actually grows its way quite nicely, pulling this soft catheter all the way to the blood clot. Once we get there, we can pull a vacuum and we can actually suck the blood clot back out and then remove the entire system out from this system. So we actually are going to be trying this out in an animal model next week for the first time. So we kind of have a few updates to it. You saw probably that this kind of steering component is a little bit larger. It's now down to pretty much the same size as the growing component itself. So we'll see how this actually works once we have all these other sort of factors in play. Great, so that's sort of the majority of what I wanted to show you for these growing robots. The last thing I wanted to show with these growing robots is I always get the question of how do you get this back out? How do you retract it? It's actually quite not obvious the best way to do it. So I wanted to show just one solution that we have here. And the reason I want to say why it's hard to pull this back is you imagine you have this kind of long inflated structure. If you try to just pull the internal material, it's going to buckle, right, if you're over a certain length. And you don't just want to like pull the whole thing back out. It can kind of work, but now you've kind of negated the benefit of this friction-free eversion or growth on the way there. So what we have here is a pretty simple design. And what it is we have this extra channel that we call a retraction channel that runs along the body of the robot itself. And what we do is when you pressurize this extra retraction channel from this inside here, we can see that it inflates and it basically will start to pull that inverted material backwards. So it's a little bit confusing to see. We've made this animation, but what you can see is that with this type of design, if you were to just pull the inverted material back, through this kind of constrained environment in the bottom video. You can see it results in this kind of movement. You destroy the environment. Now, if we use this retraction channel, we can perfectly reinvert the material, and it's not going to move relative to the environment at all. We get this sort of perfect reinversion. And it scales quite nicely as well. You can see some examples of 3 millimeters all the way to 15 millimeters. And the kind of key aspect of this design is this sort of kink that's being called out up at the tip, so that the air that you're inflating into this retraction channel doesn't really escape past this kink. It acts as kind of this moving kink valve, basically. And this is how we achieve this retraction, even at a very, very small scale. And I think the videos are basically just showing we can stay very soft, we can have external loads on top of this robot, and because we're reinverting versus pulling at the base, like you see here, we are still able to perfectly kind of reinvert our robot body back to its original location. Great. Okay, any questions on this part before I keep going to the next section? I know people asked a few things. Yeah?
Yes, sorry. You mentioned that you could add sensors to do like closed loop control.
Yes.
I wonder what sensors you would add, and also like, would it be possible to add a camera?
Yes, very good questions. So we have tried different types of sensor integration into these robots. The trickiest part is because the material like folds back on itself at the tip, they have to be quite robust to kind of this eversion process. So we've done a few different things. We've tried sort of flex sensors to try to be able to detect the curvature of the robots and maybe do some type of obstacle detection. With the ones that we're doing here, where maybe we would want closed loop control of the liquid crystal elastomers, temperature sensors could be nice, for example. We have put a camera at the tip as well, and there's other groups that have done this. And then maybe you could just use SLAM or something else to help with, robot control. I think there's many different opportunities for sensing here. I've seen some people look at pneumatic sensors along the length of the robot as well. But I think it really depends. Do you want to control the position, the shape, the forces? And that will probably determine what type of sensors to include. But it is tricky to integrate. And also, if you increase the thickness of the wall too much, the pressure required to grow also increases. And so that presents more challenges as well. Yeah, in the back and then here.
Do you draw any inspiration from a biological world, like for the pressure control, the temperature control? Like, what are the interesting state-of-the-art competitors as far as biological systems?
Yeah, that's a very good question. I mean, the original robot is inspired by vines and biology. But in terms of the controllers, that's a good question. I know that there is this like circumnutation, I think, that vines do in sort of the way that they grow. They have this like interesting method of oscillating and growing from what I've read. But yeah, I don't know exactly in terms of sensing and control if there's, that's a good point. Maybe there's a good biological analog.
How do worm creatures, they must use temperature, right?
Yes, that's a good question. I don't know exactly, but I think it's something that would be, interesting to think about. I know that some, right, maybe are grow towards light, for example, but I think it just depends then on the application, whether the mechanism makes sense for these robots and stuff as well. But definitely something interesting to think about. Yeah,
I was wondering how in my mind, like if you're pushing the air channel up as it's averting, like maybe it would buckle at some point. How does the internal structure gap pull on the internal channel?
Okay, so I see. So when I said that it's like pulling this catheter or working channel with it, so the way that we tend to do it is that the inverted material, the tip of that is attached to the tip of the catheter or whatever tube you want to pull. And that way, as it's growing, it's basically pulling in tension, and so it'll pull it along with it. So you're not really pushing. We like physically connect them, basically. So it's always pulling, and you don't have to push. That's the idea. Great. Then yes, I will continue on to talking a little bit about another area. So thinking about some of our soft wearable robotic systems. Here, what we've been really motivated by is thinking about stroke rehabilitation. So in general, stroke can cause many different complications, including contractures of the joints. You can see some examples of what happens kind of after a stroke up here. Oftentimes, people can use what's called continuous passive motion therapy, which basically has been shown to help reduce the spasticity in the muscles, improve the range of motion, and it's basically, even though the person is not actively moving their joints through these range of motions, someone or a machine can kind of move them through these range of motions for them while they remain passive. But there are kind of a number of drawbacks to current robotic systems. And so what we've been thinking about is trying to capture kind of the functionality of these continuous passive motion therapy devices in the form of a system that could be soft and worn at home. So you can see a few examples of some rigid systems here that tend to be bulkier, grounded, maybe only found inside a physical therapy's office. And there are some examples of soft robotic systems, but they tend to have more limited range of motion, as well as oftentimes there can be kind of parallel loading to the skin, which can be not quite that comfortable and can be kind of challenging to put on and take off. So the system that we have here is this we've been focusing on the wrist, which I know from talking to people, other people are interested in the wrist for various reasons as well. Oftentimes I think people tend to focus on the fingers, which is important, but oftentimes in stroke in particular, if their wrist can't move through these range of motion exercises, then doing dexterous manipulation is quite hard. And so, actually, if you guys have the pump still, I have an example of the actuator. If people want to try this out as well, we can swap out the demo in a minute. But the device here is quite simple. We use these textile pneumatic actuators. There's one on the back of the wrist and one on the front. And the idea is that as we inflate them, right, we can get this sort of bending motion and do wrist rehabilitation. And so these actuators, inspired from previous work, they're relatively simple. We have this inextensible fabric on one side, and then we have this extensible fabric with these straight stitches on the other. And we include these pleats as well to kind of control the bending and where the bending occurs, and as well as kind of the overall moment generated. And we can align this with kind of the joint of the user. And so, I guess, do you want to pass it back up and I can switch out the, great. People want to play around with this. I think it's helpful just to kind of play with it and see what the torques are that can be generated. So you guys can kind of just pump it up yourself if you want. I guess I haven't really seen what the limit is, but so maybe don't over-pressurize it, but you can kind of play around with it then and see, maybe I will just pump it up, and then you guys can play around with it a little bit. How's that sound? So that's one example of one of the actuators. And so for this type of system, right, most of the time here, we start with a model. We want to describe the amount of torque that the actuator can provide as a function of the pressure as well as the bending angle. So here, really, we just made a few different assumptions. We did this lumped parameter modeling. We assumed that the pleats could be modeled as this lumped spring. And then we had a couple fitted parameters here as well, C1 and C2. And you can see basically the plot, ultimately what we're interested in is, based on the bending angle and the pressure, what is the torque that we can generate. And the idea here is we want to make sure that we can generate enough torque to actually be able to extend and flex the wrist of a user, even if they have these kind of spasticity and increased stiffness of their joint. So the markers, these kind of small black triangles, represent this sort of passive, this stiffness that we would need to overcome to be able to actually do this continuous passive motion therapy. And we can see how the generated torques will vary as we change the width of the actuator. So that's what these different lines are. And that will help us design, what size, geometry, dimensions we need to actually design this device. So here is, after we have the actuators themselves, we also have to think about integrating them into a sleeve itself. So here, my PhD student came up with this idea of having kind of this wrapped design. So oftentimes people have kind of one good hand and one hand that is affected. So it's kind of hard to use both hands to get something on. So we thought, instead of having something that maybe you slide on like a glove, if instead all you have to do is place your affected hand on top of this device and you can use your good hand to do all of the wrapping, it might be easier to kind of don and doff the device itself. And then with this, we basically did some simple first characterizations looking at the overall range of motion that we can achieve, which is quite high compared to previous devices in both flexion and extension, and we can do so at relatively lower operating pressures. And since then, what we've been thinking about is how do we actually integrate sensing? So again, we can do some of this more closed loop control of the system. And we've been thinking more about starting to do evaluations with the target population in terms of both functionality as well as just user accessibility. So I did want to talk a little bit about this integration of sensors. In particular, we've been thinking about using off-the-shelf flex sensors for these types of devices. Oftentimes people think about using EMG sensors or other physiologic sensors in wearable devices, but there are some challenges with these. And so we've been thinking about integrating purely flex sensors to use for kinematic sensing of the device. The idea being if we can use this to understand the angle of the joints of the user, we could start to use this for closed loop control. So maybe we can modulate, for example, the amount of assistance we provide to the user just based on understanding their input into the system. And so here what we were interested in is using a commercial sensor and integrating it directly into a fabric sleeve in a way that we could have this very simple and repeatable sensing capabilities. And it turns out, so it sounds quite simple. You buy a commercial flex sensor, but I don't know if people have played around with these. They're less reliable than you would think. And now that you have them integrated with this human, it becomes even trickier. And so it turns out that what we need to do is try to accommodate for misalignment between the neutral axis of the sensor and the neutral axis of the joint of the user. And so you can see kind of in the schematic down in the bottom right, we actually need to be able to allow the flex sensor to translate and slide relative to the joint of the user. And if we don't, you'll end up with this, if we don't do it properly, you'll end up with this kind of buckling of the sensor itself, which is going to cause a number of issues. And so what we had here is 3 different designs. So these 3 different designs here. The first design is kind of quite simple. We have this smooth surface for sliding, and we added a little bit of increased stiffness to prevent any sort of buckling of the flex sensor. The second one, all we did on top of this was add kind of a spacer and try to reduce, and a cover to reduce friction. And the third one, we basically tried to add a patterned region, thinking that it would allow for more kind of uniform creasing. And what we did is we wanted to compare these 3 different designs and compare the kind of calibration curves that mapped our sensor signal to the joint angle, and also look at hysteresis. So here's a comparison of the different designs, and this is with no assistive device, so just the flex sensor integrated into a simple sleeve. And we can see the 3 different designs here. And on the right, you can see a comparison of the hysteresis area as well as a comparison looking at the linearity. And we can see here that basically our second and third designs tend to perform better here in both cases. And then when you put the assistive device on top of this flex sensor, we can see that this changes a bit as well. And we can see that our second design in the middle here actually performs much better across the board in terms of remaining quite linear, as well as having a relatively low hysteresis area. And so what we did here is we wanted to show that this approach is actually quite scalable to different joints as well. So it's not just for the wrist. We used the same design principle to design a sleeve for the finger, put it underneath a commercial glove that you can buy off Amazon for a couple $100. And turns out this kind of sensing method you could wear as a sleeve underneath an existing device and then use this maybe for closed loop control as well. And so here, we evaluated the tracking accuracy at different speeds, and both with and without the assistive device. So the top plot shows without the assistive device, and you can see the root mean square error. The middle one shows with the assistive device on top of it, and the bottom one shows for the finger with an assistive device on top. And we get pretty accurate predictions of joint position with very low variance and over the full range of motion with our root mean square error under about 4 degrees or so in all of the cases. So this is something that we've been kind of pushing more recently, starting to think about, and now we're thinking more about adapting the control of our soft assistive devices using this kinematic sensing based on how the user is actually interfacing with the system. Great. Any questions before? Yeah, I go to the last section.
I guess I have a high-level
Sure.
question. So with these like at-home care autonomous
Yeah.
wearable systems, like they show great promise and so on, but we don't really see so much of them as products. So would you say that one of the gaps might be, you talked about attachment, right? Like the placement of the sensor for different bodies or the actuator and for targeting the specific, motions. It sounds like they require an expert's intervention regardless. So it's not like devices that you can just put on and start training without necessarily knowing the correct attachment. Would you say one of the gaps might be, and are you planning to address, that these should still require the intervention of some expert assistance for the user to be able to do this at home,
Yes.
like portably and so on?
Yes, okay, so very good questions, and I think there's kind of multiple questions in here. So maybe the first thing I would say is, yes, I think that there should always be some input from the clinician in the loop. We've talked to people where you could imagine one model is maybe the first time you're gonna use it, you go into the clinic, they show you, they do all the fitting, they get it all set, and then you can go home and everything from there you can kind of do yourself, with the idea that all the data could be sent back to the clinician. They could then send information back to the device on what types of exercises you should be doing, and so there's still this like kind of human in the loop here, exactly. I also think that it's our kind of job as the robot designers to try to design them to be somewhat agnostic to how you put them on. Maybe there's going to be a little bit of initial training as you move through the device. Maybe you need to use a little bit of machine learning, for example, to fit a few parameters, but then maybe it can kind of be used from there. And then I think your question about why don't we see more products? Or maybe, I mean, you saw that in this one here, there actually is a product, it does exist, and yet I don't think people use it that much. And that is another thing we've been talking to people about. I think it's still an open question as to why people might even buy the device but not always be interacting and using them. And I think this is something we need to still get more information and data on. I think there's a number of different challenges. Engagement, I think, is probably one thing too. I think people like the idea of gamifying things. So if you can get points or there's something to keep you engaged with it, it's probably not that exciting to just try to use it and open and close your hand, for example, which is why I think we also think that maybe this passive motion therapy, where maybe you're just sitting on the couch and it can go through these range of motion exercises, could be useful. But yes, I think there's still a lot of research that we need to do to better understand why things aren't becoming super successful products necessarily. Yeah. Great. Okay. Great, then I think I will talk about the very last topic area, which is the soft haptic interfaces. And what we've been interested in is understanding really how we can try to provide salient haptic cues in a wearable and portable form factor. And the reason we are interested in this is because we think haptic guidance could be quite useful for a number of different tasks. For example, if you're trying to do rehabilitation exercises, maybe you could use haptic guidance to guide you through direction cues. So what direction should you move your arm, your wrist, your hands, for example? Maybe just with some simple guidance, you can get those cues. Maybe it's feedback on task performance. So I don't have any slides here, but if people are interested, we work a lot on interfaces to teleoperate our continuum robots, and maybe you need information on the environment in the form of force feedback, and so we've worked on some of those interfaces as well. But for these wearable interfaces, something we've been thinking about is you want to maintain kind of this wearability, this comfort, but you also want it to be practical, you want it to be portable. A lot of pneumatic systems, as you can see, one of our examples from my lab on the far right, you can kind of see off in the background there all of the valves, right? The pneumatics controls the regulators. It can become quite a bulky system that maybe isn't able to be sort of truly portable. And so that's something that we've been very, very focused on recently. And the one way we've been thinking about this is using, again, these thermally responsive actuators, again, these liquid crystal elastomers in this case. And we've been thinking about, they have these really large elastic strain limit during actuation, but one of the main challenges with these is that there's this trade-off between the force that you can generate and their response speed, right? They're thermal actuators. The cooling rate is really going to limit how fast you can operate these. And so the idea behind this project here is thinking about, can we have a very simple solution to overcome this force bandwidth trade-off? And the solution that we have here is basically taking many of these thin LCE units, bundling them in parallel to one another so that you can increase the amount of force, and then having very low flow rate cooling, basically cross flow across them to increase the bandwidth. And so here you can see an example of one of these kind of actuators in the bottom left. And we started again with some simple modeling here. In this case, an electro-thermomechanical analytical model to predict the temperature, the blocked force, and the cooling rate based on the input power and the geometry of the liquid crystal elastomers. And here we looked at both a model for passive cooling and active cooling. And what we have here then is the results of the modeling plus the experiments. So kind of walking through them, the top left plot, we can see based on the input power, what is the force that we are able to achieve with just a single one of these LCE units as we vary the thickness, right? So if we increase the thickness of the LCE, great, we can get higher force. But if we look at the plot to the right of it, we can see that as we increase the thickness, this is also going to increase the cooling time, as I mentioned. You can see in the plot the passive versus active cooling. So even really low flow rate, cross flow, we can get much, much faster cooling times. But there's this inherent trade-off, right, between the force and the speed. So in the bottom plots, what we can see is now what happens if we take multiple and we bundle them together. And so now we can see the power versus force plot. And as we increase the number of these units to 4, for example, here, we can get much higher forces. But if we look at the cooling plot on the bottom right, we can see that our cooling time will remain the same even as we bundle more of these together in parallel. So the idea is quite simple. We take many of these thin units, bundle them in parallel, add a little bit of cross flow, and now we can actually create something that can operate in the forces and the speeds that we need for some type of haptic feedback. So the bottom left plot is basically what we call these set of design guidelines that we can build using the simple models. And the idea behind this is given an application, so maybe you're interested in some other application. Here we were looking at skin stretch for haptic feedback. We also looked at making a little like inchworm crawling robot. So no matter what the application, you probably have a force requirement and you probably have a speed requirement. So that's what this design guideline is showing is if you know the cooling time that you would need to meet and you know the maximum force, then what this design guideline shows you is that each of these dashed lines shows how many LCE units you would need to bundle, and the color represents the thickness. So this allows you basically to pick the thickness and the number to meet your force speed guidelines for the particular robot. And you can see an example here of our skin stretch device, so it can provide just a little bit of a haptic cue to the user, maybe to provide direction information or feedback on how they're doing in a particular task. And as we change the input power, we can change the amount of contraction, and so the amount of kind of skin stretch that the user might actually feel on their arm. And then, so this is using these liquid crystal elastomers. And the very last thing I want to show is another thermally actuated haptic device, this time using SMA, so shape memory alloy. And this time, instead of a skin stretch, we were interested in basically normal forces being applied around the wrist of the user, but again, in a wearable form factor. And here, using SMA can be quite tricky. They have very low strain, about less than 5% typically. So working with our collaborator, Jae-Sung Ko, they have developed these types of actuators that use SMA. You can see a schematic of it up at the top. The idea is that it basically amplifies the amount of displacement. So you have maybe a small amount of displacement of the SMA, but you can actually get amplified displacement of this actuator using this nice flexure mechanism. And we can use these, we can independently control them to get different types of haptic cues. And here, again, we were thinking about the different parameters that we can vary based on the design requirements. So we can vary the diameter of the wire of the SMA, the number of the wires that we put across, as well as the ratio of the lengths of the wires to this compliant mechanism. And this will change our design parameters in terms of how much normal force do we want to achieve, what are the displacements that we need, and then the frequency of actuation. And so, I should show the video. Here are the actuators in action here. So you can see them actually moving. So as the SMA contracts, we get this displacement of the actuator. And we looked at adjusting the frequency, force, and the pattern of actuation. So what we worked on is how do you integrate these actuators now into a wearable device? It turns out there's quite a lot of nuances to actually making this device actually transmit the force to the user. So a lot of this has to do with the selection of the materials and the fabrics themselves. So for example, we need to use a relatively inextensible fabric on the top layer so we can actually transmit the force to the user. And then we use a stretchy fabric on the inner layer that's next to the user here. And we also looked at how much space you need sort of between the actuator and the fabric themselves and how that affects the output force. And so here you can see an experiment varying that kind of gap, that width. And this just shows the experimental setup where we have a force torque sensor and kind of a mock forearm, and we're measuring the forces based on different preloads around the user, because you also, again, don't know how much are you going to load it around the user, and you want to make sure they can feel a reasonable amount of force, even with varying preloads. And so here are some videos of the different types of haptic cues. This is kind of looking straight down on our system. So here in the top left, you can see that we can do these kind of clockwise, counterclockwise cues that people can interpret quite well as these different directions. So you could imagine this might be useful for guidance, maybe of rehabilitation. We actually also, our collaborators did a demo where they wanted to have people even just walking down a street, and you can get these direction cues of which directions to actually turn. We can do it at different speeds, so this is like a slower clockwise, counterclockwise. And then we can also do what some of my favorite ones is actually the squeezing. So we can do squeezing and tapping at different rates and with different amplitudes. And what's nice about this is it actually feels quite good. I know I don't have an example of the device, so you'll have to believe me. But a lot of people ask, why not just put small vibration actuators into a wearable device? But I don't know about you guys, I feel like people do not actually like vibration. It's kind of annoying if it happens over and over. No one really likes it. People tend to turn it off, right, on their watches. But this feels quite nice, actually, the kind of simple squeezing and small tapping around the wrist. So we did a very simple kind of haptic perception study where we tried to determine how well can people identify the location of these 4 different taps and how well can they distinguish the different cues I was showing. So like clockwise, counterclockwise, squeezing, and how well can they perceive this. So in the middle plot, what it's showing is basically just that even at high, medium, and low amount of force, people can distinguish the exact location of the taps with very, very high accuracy, near perfect accuracy here. And the confusion matrix on the right basically shows, if you look at the diagonal, that people's predicted pattern matches very closely to the actual pattern that we were displaying to them, even across seven different kind of patterns of these actuators. So again, kind of some preliminary studies here, but I think potentially useful in thinking about new methods of haptic guidance and feedback. Okay, so to wrap everything up, kind of coming back to my original slide that I showed with these kind of manual methods on one side and our kind of traditional current robotic systems on the other. Hopefully, I've showed a little bit of how we've been trying to think about starting to fill this gap in between with both the design of our soft robots and our haptic interfaces. Talked a little bit about both on the spectrum on the top of our soft continuum robots for surgical applications, and on the bottom, these kind of soft rehabilitation robots. And I didn't get to talk about all of our different user interfaces, haptic interfaces, but here are a few others that I'm always happy to chat with people about. And before I finish, of course, all of this work was done by my amazing lab, students, postdocs, collaborators, and have to thank the funding sources as well. So yes, thank you guys all for showing up and coming, and yeah, happy to take any other questions. Great. Yeah?
For the LCE haptic device, it was heaters at the base.
Oh, yeah, so actually it was at the base, that was actually just for the cooling. So the heater is actually, we gold sputter on top of the liquid crystal elastomer, and that's for the heating. Mm-hmm. Yeah. Yeah.
I guess why gold sputtering?
Yes, good question. So for each, so yes, you can talk to my students and postdoc.
A stretchable conductor.
Yes, so we tried many different, that's one thing with LCEs that we found is that depending on the application, the use case, the heater that we used actually varies quite a bit. So they did try many other types of heaters, and for that application, the gold sputtering did work the best. We tried gold sputtering for the growing robot application, but because of this E version, this was quite tricky, and we ended up with the PDOT. But it definitely depends on the application for us, which one seems to be most reliable and work the best. So, yeah.
I guess for density wise, I was gonna ask, like, SMAs show quite nice power density at large, like for any type of, as an actuator, as a thermal actuator, and they vary at different, diameters, nice and separatable. Now, what was it's a more general question, like why did you go forward with LCEs and that skin stretch device instead of SMA?
So it's a good question. I think they both have their merits. In particular, LCE has much higher actuation strain. And so I think depending on how much contraction you actually need, maybe LCEs can be better. It depends though. I also think that LCEs can be fully soft. I mean, I guess if you make the SMA small enough, they could be and LCE, you also have this ability to make, because it's a material that like our collaborators are making, you can shape, like we laser cut it, you can make different shapes and stuff. So maybe it just gives you a little bit more flexibility. But I don't think, that one is always better than the other. I think it does depend. Yeah. Great. Yeah.
For the thought, I have two questions. So the first one is, when you measure LC haptic devices force, how would you measure it? Is it like block force or lifting?
Okay. So for the for this part here, I see. Okay. Oh, here, yes, blocked force. For these? Yes. Yes. Block force.
Okay, and then the next question is for your next SMA-based haptic device. You said you can tune the frequency, right? How much frequency were you able to get to?
That's a good question. I don't know off the top. I think I think we set like, okay, we want to operate up to 5 hertz, for example. How would we need to size the SMA to meet that requirement? But I don't think we actually looked at what is the fastest that we can do. We just thought for our application, what is the rate we want to hit and how do we design for that? So I don't know if I have an answer to what's the maximum.
So is it, so my understanding is that your F44 structure applies some sort of like stiffness. That's how SMA can boost on its frequency. Is that correct? Or?
Yeah, so basically, so as the SMA contracts, we get this displacement of the FR4. And so mostly here, amplifying the amount of displacement that we get. So we actually get a meaningful amount of force applied to the user. But yes, and then there's this inherent stiffness of it as well. I think, I don't have it in here. We do have, now that I think about it, some Bode plots of the frequency response here, but I don't have it here, I'm sorry, but I'm happy to chat after and show you some of these. So you can see, how it helps with that as well. Great. Okay. Well, thank you guys. Happy to, chat more after then too.